Exercise 1106 is about solving trig equations. So I'm just going to go straight into some examples. You can see I've got my exact value triangles here. I'm going to need those. Our first example is to solve 2 sine theta equals square root of 3. So of course the first thing we want to do is divide by that 2. So we've got sine theta equals root 3 on 2. Now once you're in the form where it says sine theta equals, then you want to consider these steps. So you use your exact value triangles or your calculator to find the principal solution, or the first solution basically. And then you can use either all stations to central or a trig curve to find further solutions. So let's see what that looks like. So first of all, root 3 on 2, it is sine, so opposite hypotenuse, so 60 degrees is my principal solution. So 60 degrees. I could have gone shift sine root 3 on 2 in my calculator. So my next step now is to find other possible solutions, because there are more solutions to this. We know from our all stations to central that we have various situations in different quadrants. So all stations to central, this is sine and it's positive. So we could have a solution here, which is the 60 degrees, but we might also have another solution over there. Well, in fact, we do have another solution over there. So where I get 60 degrees here, remember sine is that height on the unit circle. So if I have that exact same triangle drawn over there, then that height is exactly the same. So if this is 60 degrees here, then we want to know how big is that angle. How far have we gone from 0 around to this line? So it's also equal to 180 minus 60 in this quadrant, in quadrant 2. So, or equal to 180 minus 60, which is 120 degrees. So that's 2 solutions. Now, technically speaking, we could keep going round and round and round the circle and find infinitely many solutions for this equation. There are infinitely many. We could also be asked to find it in a negative region, so we could be going clockwise around to find more solutions. So clockwise, this solution here would be the negative of 180 plus 60. So negative 240 degrees. So in your calculator, if you go 2 sine 60 minus root 3, just minusing root 3 off each side here, that should equal 0 if you're in degrees. If you go 2 sine 120 minus root 3, you're going to get 0 again. If you went 2 sine negative 240, so that's the negative 180 and another 60 minus root 3, that's going to give you 0 too. And there are infinitely many numbers that you can put in there for theta. We were asked to find the solutions between 0 and 360. So our solutions are just this 60 and this 120. So this is just a side note. This is not part of my solution, but you can use this to check your solution. Now, I did say you could also do it with the trig curves. So I'm just going to show you how to do that. So I've drawn here a sine curve. So what we want to know from here is, when does sine theta equal root 3 on 2? Now, root 3 on 2, that's around about 0.866. So this is 1. So we're saying, when is the y coordinate of this curve equal to root 3 on 2? So root 3 on 2 is around about there somewhere. So everywhere that the curve, the sine curve, touches this pink line is where we have a solution. Now this is our 360 degrees here, and we were only asked to find solutions up to 360 degrees, between 0 and 360. So it's just those 2 solutions there. But if we were asked for more solutions, you can see it's going to keep happening over and over and over again. Now, what we do here is we use the symmetry of the curve. It's very, very cool. So because that is 60 degrees there, that's 60 away from 0. Remember, this is 90 and this is 180. Because this distance is 60, this triangle over here is the same size. So this is 60. Okay, from 180, it's 60 back. If that is 60, then that is also 60. So that's where we have 180 minus 60 equals 120 at that point. If I was to do the same thing over here, it would be the same thing again. That's 60 there, then that's going to be 60 along there as well. Okay, this little gap is 60, that little gap is 60. And that's going to happen over and over again. This little gap is 60. So if we were asked to find solutions over 360, then we can go 360 plus 60, that gives us another solution. And if we were to go negative, we could find these two solutions here. So this is negative 180, this is negative 360. Here's that triangle, that little gap is 60. This is negative 360. So that answer negative 300 is actually also another solution to that equation as well, but outside the domain that we're being asked about. So this 60 here, that's that negative 240 that I mentioned above. So negative 180, another 60 makes negative 240. So you can see there are infinitely many solutions that go on forever and ever. So example 2 is tan theta plus 1 equals 0. So the first thing I'm going to do is minus 1 off each side. So tan theta equals negative 1. Now I can use my calculator if I want to find the first solution. Now I've just given us a domain to think about our solutions on. So if I put that into my calculator, it gives me a solution of negative 45 degrees. And that is our principal solution, negative 45 degrees. But remember, there are more solutions. So firstly, what we can do is actually find out what would happen if theta was positive 1. So we do our all stations to central, all stations to central. Now, we've found that 45 degrees. If it was positive 1, that would actually give us 45 degrees as well. But because it's tan and it's negative, we need to consider which quadrants we're in, okay? Tan being negative, not here, yes, not there, yes. So we're in quadrants 2 and 4, quadrants 2 and 4. Okay, 1, 2, 3, 4, we're in 2 and 4. So we're looking at 45 degree angles in quadrants 2 and quadrants 4. If we'd gone shift tan positive 1, we would have still got the 45. Now that negative 45, that's down this way, negative 45. Now I have said I want solutions from negative 180 and positive 180 in that region. So that negative 45 is one of our solutions, it's inside there. So if I go this way for my negative angles, once I hit negative 180 I can stop and there are no more solutions there. For my positive angles, I need to go this way round. And we said it was in this quadrant as well. So that 45 degrees to the x-axis there will give us another solution. And that's going this way, so we're positive. So theta equals 180 minus 45 to find this angle here. And that's 135 degrees. So those are our two solutions. Okay, for the second method, I have drawn my tan curve, and I've done it from negative 180 to 180 as I was asked, and I'm asked to find where does it equal minus 1. So if I just draw a line horizontally across here at minus 1, because when we're asked for that, we want to know where is the y coordinate minus 1. So that's minus 1 there. Now I could go shift tan positive 1, or I could use my exact value triangle to find that 45 degrees for positive 1. So that means to here, this distance is 45 degrees. That gives me positive 1, which means that this distance for this point is going to be negative 45 degrees. It also means this distance here is also 45 degrees. So there's our 135 that gives us that second solution. So there's our two solutions, negative 45 and 135. Now, most books I find these days do tend to use the first method in their explanations. This is actually the method I used when I was at school. I didn't really even learn about all stations to central when I was at school, to be honest. We just used curves. I quite like it, but you will find this other method, this first method, is what comes up a little bit more often. Just do whichever method works for you. So example 3 looks at what happens when you've got a square. So we've got 2 sine squared x minus 1 equals 0. Now we're also now in radians. We're told that x has to be between 0 and 2 pi, so we are in radians. So I'm going to plus the 1, so 2 sine squared x equals 1, divide the 2, sine squared x equals half, and I'm going to square it each side. So sine x equals plus or minus the square root of 1 over the square root of 2. So positive or negative 1 on root 2. Okay, let's find our principal solution. So the first one is from this triangle. Now let's just put the angles into these. This is normally 60 degrees, so this one up here is pi on 6. Remember that 6 is opposite 60. This is normally 30, so this one opposite is pi on 3. This is normally 45, so this is pi on 4, and this is also pi on 4. Now 1 on root 2 is from this triangle, so x equals pi on 4 is our principal solution. Now, because this is plus or minus, that means that we could actually be in all 4 quadrants. Okay, positive or negative, it does not matter. All 4 quadrants. So let's draw it. We're in all 4 quadrants. I'm not going to write the all stations to central because it's positive or negative everywhere. Now, pi on 4 is there. It's the same as 45 degrees. Which means there's a second solution here where that's pi on 4. There's going to be a solution down here where that's pi on 4, and there's going to be a solution down there where that's pi on 4. So let's have a look. Remember, this is 0 pi on 2, this is pi, this is 3 pi on 2, and then back round to 2 pi. So 0 to 2 pi, as we were asked for, means we're starting here and we're looking for any solution we come across until we come back here. So there are actually 4 solutions here. So our second solution is this one, which is pi minus pi on 4. Okay, that's the second one. Our next one is this one, and that's pi plus pi on 4. And then this one here is going to be 2 pi minus pi on 4. Now remember, in your calculator, if you want to go 1 minus a quarter, you can, or you can just use basic fraction calculations. So pi on 4 is our first solution. Pi minus pi on 4, this is 4 pi on 4 minus 1 pi on 4, so that's 3 pi on 4. 1 minus a quarter is 3/4. 1 plus a quarter, so 4 on 4 plus 1 on 4 is 5 pi on 4. We must use improper fractions. You cannot write 1 1/4 pi, that does not make sense. 2 pi minus pi on 4, so if we want this over 4, it's going to be 8 on 4, minus 1 on 4, so that's 7 pi on 4. So using that second method, we want to draw our sine curve, and it could be 1 on root 2 or negative 1 on root 2. Now, it doesn't really matter where you draw a line across. It's around 0.7, as you don't really need to know that. That actually doesn't matter too much. But there's positive 1 on root 2, and here's negative 1 on root 2. Okay, you can just draw those lines anywhere, really. It is just rough working out, so it doesn't really matter. What you need to know is there's one there, there's one there, there's one there, and there's one there. And again, those distances will be the same. So if that is pi on 4 here, then this one here is pi minus pi on 4. That distance there and that distance there have to be the same. So that's our 3 pi on 4 solution there. This one here, that distance there will be pi on 4. Now you can see I haven't drawn it accurately, it doesn't really matter. So that's our pi plus pi on 4, so that's our 5 pi on 4. And this solution here, that distance there is also pi on 4, so that's our 7 pi on 4 solution there. So 1, 2, 3, 4 solutions. So when it is a squared, sine squared, you will get twice as many solutions because you'll get one in every single quadrant. Okay, in example 4, we've actually got a quadratic equation. So just like normal with a quadratic equation, I want to get everything onto one side first. So cos squared minus cos x minus 2 equals 0. I could use the quadratic formula, or I could factorize it, and this one is factorizable. So it multiplies for -2, it adds for -1. So +1 and -2. So cos x plus 1 and cos x minus 2 equals 0 are my two solutions. And now I just need to solve each of those separately. So on this one, my cos x would equal -1. And on this one, my cos x would equal 2. Now, cos x never, ever, ever equals 2. It's always between -1 and 1. So for this one, I have no solutions. Okay, it's possible I could have solutions for both. In this case, I don't. There are no solutions where cos x equals 2. Now, cos x equals -1. Now, that's not from our exact value triangles. You can do your all stations to central. I actually find one when it equals -1 to be a really useful one to use the second method. Remember, we can always use our calculator. We need to be in radians. So we can see here that there is a solution at pi. We can recognize that as pi. Now, if for example, this came up and you didn't recognize that as being 2 pi, which it is because I've just doubled my answer, what you can do is divide out pi. If you're in radians and you divide out pi and get 2, then it's 2 pi because we divided out the pi, but the pi is technically supposed to be there, so 2 pi. But that's just a side fact. So here, x equals pi is one possible solution. Now, if we're doing all stations to central on this one, because it's -1, remember cos is the x coordinate on the unit circle, so -1 is actually this point right over here. So if I was to draw the unit circle, the angle is to there. Now, we were also asked to find any solutions from pi to negative pi to pi. So in actual fact, we can go this way round to negative pi as well. So negative pi is a second solution. So using our second method now, we're saying, where does it equal -1? Now, -1 is right down here. Now, for solutions involving 1, -1, and 0, I do quite like this method a lot more than that method. This method is great when it's not 0, 1, or -1. This method I find really good in that situation. And we can see right here, there's our pi, and there's our negative pi. Those are our two solutions where it's equal to -1. Okay, in example 5, we've got tan of 3x equals √3. Now that 3 does involve another layer of intricacy. What it means is we actually need to go round the unit circle 3 times. So 0 to 2 pi is normally once around the unit circle, but that 3x tells us we have to go 3 times around the unit circle. Because if you multiply all of this by 3, if you go times 3 on all of those, 0 times 3 is 0. This is 3x, which is what we're talking about, and 2 pi times 3 is 6 pi. So that 3x has to be between 0 and 6 pi. So we're going around the unit circle 3 times. So the first thing we need to do is look at our exact value triangle or use our calculator to find the first solution for 3x. I'm just going to come down here to write my solutions. So the first solution is, where does tan 3x equal √3? So √3 over 1, so it's this one here. So it's pi on 3 is our first solution. Now at this point, do not divide by the 3 yet. Find the remaining solutions before you divide by 3. So I've just written that there. Find all solutions from 0 to 6 pi before dividing by 3. That's really important. If you divide by 3 now, you will almost certainly make mistakes. Okay, so let's draw all stations to central up here. So it's tan and it's positive, so all stations to central. So we're looking here, tan is positive here, and they're all positive up here. So we've got pi on 3 there, which is that one. And then in this quadrant, we've got this angle here where that's pi on 3. So we've got pi plus pi on 3. Now it is okay not to write that there, to actually start right there writing 4 pi on 3, that's fine. But I'm going to just show all of my working out here. So that's once around the unit circle, and then we go around a second time for this next solution. So that's going to be 2 pi plus pi on 3. Now it's going to be 2 pi plus those. Each of these added 2 pi gives us the next solution. So that was 2 pi plus this one. The next one, which is all the way around and back to here, is 2 pi plus this one. So that becomes 3 pi plus pi on 3. Okay, so go around 2 pi, another pi, and another pi on 3. So that's twice around the unit circle. Okay, I'm running out of space here. Let's just go to the next line. So let's keep going round. So I'm round to 4 pi plus pi on 3, which is 2 pi plus this one. So if I add 2 pi to each of these now, I get my next 2. So that's 4 pi plus pi on 3. And then 2 pi plus that one is 5 pi plus pi on 3. So going around the unit circle, this one is we go around 2 pi, we go another 2 pi is 4 pi, we go another pi is 5 pi plus pi on 3. So we've now gone 3 times around the unit circle, which is what we needed to do. These are all of our solutions. Now, next thing I'm going to do is actually just simplify each of these first, and then I'm going to divide by 3 after that. It is possible to skip one of these lines, but you can't skip both of them. So this one, 1 plus a third, 3 on 3 plus 1 on 3 is 4 pi on 3. This is 6 on 3 plus 1 on 3, so 7 pi on 3. This is 9 on 3, so 10 pi on 3. This one is 12 on 3 plus 1, so 13 pi on 3. And then this one is 15 on 3, so 16 pi on 3. So these solutions here go from 0 to 6 pi. But our final answer for x is it has to be between 0 and 2 pi. So this is where now we do the dividing by 3. So x is equal to each one of these divided by 3. Now none of these numerators are multiples of 3, so nothing's actually going to simplify any further. So it's really just multiplying the denominator by 3. If I divide by 3, it's the same as multiplying by 1 on 3. So I get pi on 9, 4 pi on 9, 7 pi on 9, 10 pi on 9, 13 pi on 9, and 16 pi on 9. Now I'm not actually going to do that one using the second method, but by all means, if you'd like to do it, go for it. For this last example, we're back in degrees again. Now this one is actually, none of the ones in the textbook have this, but in year 12 you do need to know how to do these, so I thought I'd have a go at one. So 2x plus 15 is in our brackets here. So let's just adjust our domain to work out the 2x plus 15. So first of all, let's just double everything here. Notice we're back in degrees. So our 2x is up to 720, from 0 to 720, so that's our 2x. But we have 2x plus 15, so we need to add 15 to each of those. So 0 plus 15 is 15. This is our 2x plus 15, and 720 plus 15 is 735. So we need to find all solutions where 2x plus 15 is between 15 and 735 degrees. Okay, it's all in degrees. And then that'll take us back to our x being between 0 and 360. So let's solve this first. Let's divide by the 3. So cos 2x plus 15 equals 0.4. Now that's not one of our exact ratio ones, so we are going to have to use our calculator. So that's 66.42. Now I am going to make that in degrees and minutes. I'm going to round it to the nearest minute. So let's go 66 degrees and 25 minutes. So all I'm going to do with this one is use that second method, just like I just used the first method on the last one. So with this, this is a cosine curve, and I've gone just past 720 because we need it to go up to 735, remember. And we want to know, where does 2x plus 15 equal 0.4? So I'm going to draw a line across at 0.4. So remember, this is 1, so 0.4 is a little below halfway. So a little below halfway, we're going to draw it across. And we're going to work out all of those solutions. So this is that one that our calculator told us. That's our 66 degrees, 25 minutes there. So what we know is from a peak to there, it's 66.25. So if we look at this one, from that peak to here is another 66.25. And also this distance here is 66.25. Okay, from the peak to that angle. So as well as the 66.25, we've also got 360 minus 66.25, and we've got 360 plus 66.25. Whoops, missed the minutes. Okay, we've also got another solution over here, this one here. That distance from the peak is going to be 66.25. So we do have a solution at 720 minus 66.25. Now the big question is, do we have another solution over here? We needed to go to 735. So past 720, we need to go another 15 degrees. Okay, we saw that here. Now that's bigger gap than 15 degrees, so no, that's not a solution. So 1, 2, 3, 4 solutions at this point. Now we just need to solve each of these separately. So let's have a go at doing that. So the first thing I'm going to do is actually store this number into my memory. So remember, to do that, I go Shift, RCL, and then any of these ones with a letter on it, I'm going to call it A. So that number is now stored as A. Now our first one up here, well, we know we've got that 66.25 is still there, but this one's 360 minus A. So in my calculator, 360 minus alpha A, I do need to do the degrees in minutes. So 293 degrees, 35 minutes. Remember, we round up at 30. So our second one there is 293 degrees, 35 minutes. Okay, and then we've got 360 plus alpha A. Press that degrees in minutes button. So we've got 426 degrees, 25 minutes there. And we've got our 720 minus alpha A, and then that degrees minutes button, and that is 653 degrees, 35 minutes again. And what you'll see that pattern there. Okay, now that was 2x plus 15. So for each of those, we need to minus the 15 and divide by the 2. So let's minus the 15 first. Now technically you could do all of those at once. You could put this in your calculator and then go minus 15 divided by 2 and write the answer. Put this in the calculator, go minus 15 and then divide it by 2. You have to go minus 15 equals divided by 2 equals, and get the next answer, and so on. But I didn't do that. So let's minus 15 from each of those. So the first one becomes 51 degrees, 25 minutes. The second one is 278 degrees, 35 minutes. Now we're going to see this pattern come in again where that was 51. We've got a 26. That's quite an easy subtraction. Minus the 15. And then minus the 15 of this one, it's similar to that one. 638 degrees, 35 minutes. And now to get back into our 0 to 360 domain, I just need to halve all of those. So I'm going to get out my calculator for that. I will actually do it in exact form, just to get an exact answer. So this first one started with the alpha A that I had, and I minused 15, and then I divided that by 2, and then press that again. So 25 degrees, 43, yeah, 43, because it's 39, so I've got to round up. So for my second one, I had 360 minus alpha A. I minused off the 15, and then I divided that by 2, and then pressed that button again. So the third one was 360 plus A. I minused off the 15, and then I divided by that by 2. And our last one was 720 minus A. So 720 minus alpha A, minus off the 15, divide by 2, press the button. So the last one is 319 degrees, 17 minutes. And that's about as hard as you'll get. You'll notice all of those solutions are between 0 and 360. So this domain adjustment at the beginning really helped us to get those solutions. Now I'm just going to give you a couple of little tips about the exercise. With this one, for example, if you divide by tan, you will miss solutions. You do need to subtract the tan and factorize. When you get over to these last few questions, when you see this one here, it's got sine in it and cos in it. That's going to be very problematic. You can't use the quadratic formula on that. You can't factorize that as it is. But if you replace sine squared with 1 minus cos squared and use that identity, that's really going to help you with that problem.